Thank you. Thank you very much. Thanks for the invitation. I would also like to apologize because I didn't manage to attend too much of this conference, although I wanted to. But here we are. So today I will talk about a piece in a puzzle that we're trying to solve and understand and answer to the question of what field theory, both classical and quantum, assigns to a manifold that might have boundaries and corners. In fact, this talk should be called Hamiltonian gauge theories on manifold with corners rather, but since this confuses people, I will explain why corners come into play as boundaries of something else. But okay, so if you know, like the approaching field theory on higher codimensional strata, on cobordisms, has been popular in recent years, and it has been approached through the methods of higher geometry. But somehow, while working on that set of approaches, I realized that I wanted to have a more essential understanding of what is happening at the level of field theory on manifolds with boundaries and corners. So I started this project together with Aldo Riello to really get rid of like the higher technology and understand what that higher technology should help us understand in essence. And ultimately, the problem is that of describing the reduced phase space of a gauge theory in the presence of boundaries and corners. And the reason why we do this, it's because, well, this leads us to an understanding of its quantization and of its structure as a whole. Now, let's say the general knowledge is that to a codimension 1 submanifold inside of a space-time manifold, a field theory should assign some symplectic space. And this symplectic space, in the case of gauge theories, should be some sort of Hamiltonian reduction or a generalization thereof. But in fact, if you take this seriously, you realize that this implementation of Hamiltonian reduction that you need in field theory is subtle. And in fact, what it turns out is that the description, if you really want to take Hamiltonian reduction seriously, it's easier to think of it as a reduction by stages, where you essentially naturally separate what happens in the interior of your codimension 1 hypersurface and what happens at the boundary. Sorry, this arrow here, okay. So in fact, the, let's say, upshot of this is that the reduced phase space for a field theory, whenever you're considering boundaries and boundaries of boundaries, is rather than a symplectic manifold, is a Poisson manifold, possibly singular, which is foliated by symplectic leaves, which we call superselection sectors because they are a classical counterpart of the superselection sectors that people study in algebraic quantum field theory, for example. So in this talk, I will present the general approach to this problem, which works in a fairly large class of examples of gauge theory, with a great outlier being gravity, but I'll comment on that. And I want to specialize to a particular case, which is Yang-Mills theory, where I select a null hypersurface inside my space-time and apply the technique there, and realize that I get a purely Hamiltonian explanation of fairly recent, although we learned that 5 years in the physics literature is already old, fairly recent work of Strominger and collaborators about certain soft symmetries and certain scattering relations between scattering amplitudes in electrodynamics, color dynamics, and so on. As an outlook, I expect that a modification of these techniques should apply to general relativity and explain in the same way what is called gravitational memory effect. I will probably not talk about this too much today, but this brings the question of what is the right mathematics that we need to really treat this case, because there is no Hamiltonian action. So this is a work in progress. So let me begin by setting the stage how I'm thinking about gauge field theory here. For now, let's just take sigma, a compact manifold, possibly with boundary. The field content here is some fiber bundle. If you're uncomfortable with this, just take a vector bundle. I consider jets of sections. So I look at the jet bundle, infinite jet bundle of this vector bundle or fiber bundle, and I pull back forms over here along this jet prolongation map. This is a way to define what I call local forms, what people call local forms, which essentially are just forms and functions of the fields that depend only on the field and a finite number of derivatives. Interesting structure over this space is a bicomplex structure where I have vertical or variational de Rham differential over F, the space of fields, and the horizontal de Rham differential over the base. I define a form to be symplectic, a 2 form to be symplectic over here. Sorry, this P should be a 2. If it's the integral of a local form, 2 comma top, so a symplectic density, so something that I can integrate over sigma, I want it to be closed and weakly non-degenerate. So injective, the associated sharp map is injective. For those of you who are more functional, analytically minded, it's good to note that this space is generally a smooth nuclear end-tame Frechet manifold, and everything I will do will be in this setting. So because we're interested in gauge field theory, I need to tell you what a group action is, and this is the definition I will use throughout. So let's consider the space of fields I had before with a local symplectic form. I want a gauge group, so a local Lie group, which integrates a local Lie algebra, which is just the sections of some vector bundle with a Lie algebra structure that is also local. I want the action of this Lie algebra over the space of fields to be local. Here, local again means that it only depends on sections and a finite number of derivatives, okay? And then I generalize the notion of a momentum map to this local setting by requiring, by asking that I have a form, which is 0, top with values in the dual of the Lie algebra, that satisfies these properties. Now, from, well, the first equation, you see that this is a version of the statement that the Lie algebra action is Hamiltonian, but now it's pointwise Hamiltonian. I'm not allowed to integrate by parts, so to speak. And I have a notion of equivariance that sees the boundary. So higher codimension data, I call this weak equivariance. Now, a couple comments here. This pairing, so the evaluation of this one form d of h over an element of the Lie algebra is local as well. This means that this pairing may depend on higher jets, higher derivatives of the gauge parameters. Xi is in factor g. Okay, this is relevant for generality of the framework. Moreover, this momentum form H can be interpreted as a Lagrangian on something larger, on the algebroid given by the space of fields cross the Lie algebra that is acting over it. So this algebroid is an action algebroid. I'm sorry? Oh, a Lagrangian density in the sense of a 0, top form over the space of fields. So you treat G and P as new space of fields, and then this is a Lagrangian in the sense that it's a functional with values in densities over A. Not in the sense of Lagrangian submanifold, in the sense of Lagrangian density. If you integrate this form over sigma, you get an equivariant momentum map up to boundary. Okay, this is just a definition. Why is this definition relevant for field theory? Well, if I'm looking at a Lagrangian field theory over, let's say, a cylinder, where sigma now is a slice of the cylinder, or is the base of the cylinder, and I really have a Lagrangian density over this higher dimensional space of manifold over with fields F, the restriction to sigma induces a symplectic form in good cases. Okay, there are conditions. And I think of this as the geometric phase space of the theory. So let's say you're interested in Lagrangian field theory over a cylinder. You can take the variation of your Lagrangian. You will have a piece that gives you the Euler-Lagrange equations of the theory plus a boundary term. If you take the vertical variation of this boundary term, you get a 2 form, which you interpret as, in good cases, a symplectic form on the space of restrictions of fields to sigma. If you have a gauge series, that means you have a group action on F preserving this Lagrangian density in this sense. You may assume, this is not always the case, but you may assume that this group action restricts to fields over sigma. Okay, so obviously there are things to be checked, but in many cases of interest, this holds. And the last piece of information that you need to construct a locally Hamiltonian space is the local momentum form, but this is nothing but the Noether current. Okay, so out of a Lagrangian field theory, in good cases, I can extract the data of a locally Hamiltonian space over restrictions of fields to a codimension 1 hypersurface. So let's now, for now, assume that the boundary of this codimension 1 hypersurface, okay, so I'm looking at sigma as a slice inside this foliation. Let's assume that sigma is closed, it has no boundary. Now, as a consequence of Noether's theorem, physical configurations over sigma are recovered as the vanishing locus of Noether's current. But, okay, so what we know from Noether's theorem is that on shell, so when you impose the equations of motion of your theory, the de Rham class of Noether's current vanishes. Which means if you integrate over a sigma that has no boundary over a surface that has no boundary, you get 0. So whenever we can induce this locally Hamiltonian G space from the data of a Lagrangian field theory, the integral of the Noether current is an equivariant momentum map. Then, the reduced phase space, which is physically defined as the space of configurations on shell that satisfies the equations of motion, modulo the action of the group, is going to be the zero level set of this momentum map, modulo gauge. Because this is a zero level set of a momentum map, this quotient is symplectic, and this is why we say that on a codimension 1 hypersurface, in good cases, I get a symplectic manifold. Now, obviously, reduction might be singular. I will comment thoroughly on this later. I want to point out the fact that in the Fréchet setting, you don't only have the usual requirements of Hamiltonian reduction, but you have some extra requirements that need to be checked. Otherwise, this is not true. But the question now is, what happens if my codimension 1 hypersurface inside the cylinder has a boundary, which I think of as a corner component of the corner for the for M, for the higher dimensional manifold. So what fails is that the zero level set of Noether's current is no longer the correct locus. It's no longer the space of physical configurations, but it's smaller. It's smaller because you are actually imposing vanishing boundary conditions. Because you're asking that the integral of something that is only, 0 up to something exact will mean that you will have some extra conditions at the boundary. So the question is how to go about this problem. Well, it turns out that for local momentum forms, there is a natural decomposition, which is an application of a theorem due to Takens, which exactly splits the momentum form in something that vanishes in the right place, so at the constraint set, plus a boundary term. So we have solved part of the problem because now we know that the constraint set is the zero level set of something. But the problem is that this H naught is no longer a momentum map or momentum form for the whole group. Okay, so the natural question is, can I retain the fact that the constraint set is the zero-level set of some momentum map, but now for a subgroup? The answer is yes, and we can proceed to Hamiltonian reduction by the action of this subgroup. This is what we call first stage, because now the fact that we have a normal subgroup of the original gauge group by which we are quotienting tells us that, well, reduction is done in stages. So recall, we have a locally Hamiltonian G space with a momentum form for the G action that splits into these two pieces. And now we know that the physically relevant locus is just the zero of this bulk part. Yeah. It's essentially integration by parts, but you have to do it on the gauge parameters. So the point is, so let me give you an example real quick. So if you are considering Yang-Mills theory, H paired with a parameter is going to be E dA psi, where psi is an element of the Lie algebra and E is a top -1 form on sigma with values in the Lie algebra, you take the trace. Now the splitting tells you that H0 over Xi is just this guy, and D of small h Xi is D, the trace of E Xi. Yes. Okay, so you can easily see that the zero-level set of this form is configurations that satisfy Gauss constraint. So this is the shell. Whoop, sorry. Okay, so the result here is that under certain assumptions, which I will discuss in the next slide, there always exists a ideal, maximal Lie ideal, with the property that its associated momentum map is precisely the constraint set, so the zero-level set of H0. That's the first step. I call the integration of this Lie ideal the constraint gauge group, and I call the quotient the flux gauge group. Then I have a residual action over the reduction, which is symplectic by means of the fact that this is a zero-level set of a momentum map. And this action is Hamiltonian. So a version of this boundary term becomes relevant because it becomes the Hamiltonian momentum map for the residual action. We call this H underlined the flux map because in electrodynamics, this is exactly the electric flux through the boundary. It's a version of the Noether charges, the non-vanishing Noether charges. Maybe also surface charges, but these are really the integral over a codimension 2 surface charges. Okay, surface charge, very good. But you see, the slightly non-trivial point here is that this H is reduced, so it descends to the first stage reduction, and then it's a momentum map. Okay, so let's talk about what we need to make this work actually. So as rigorously, we want this, first of all, we want the submanifold C to be a submanifold, so to be Frechet smooth. We want these Lie algebras, which can be defined always like this. We want them to integrate to Lie group, which is non-trivial in infinite dimensional Lie theory. And we want the action of G naught over C to be free and proper. Now, this can be verified for a relatively large class of theories. For example, Chern-Simons, BF, Yang-Mills, at least for G compact, because there you have properness of the action. In these cases, in fact, G naught is nothing but the gauge transformations that vanish at the boundary, okay? Up to constants, in the case that you're looking at an abelian group action, then you have to add constants here. And, okay, so when you're looking at quotient, you need to ask yourself whether there are stabilizers. Stabilizers need to satisfy this equation for theories of connections. But you can see with a simple argument that there are no stabilizers for this G naught action. So Chi is smooth and the action is free. Yeah.
You know, sometimes in gauge theory people work with Sobolev spaces too. Is there a reason why you would prefer the Frechet?
I think the problem with Sobolev is that when you add a derivative, you need to go off the, right? So Frechet is more natural because you can work with smooth functions. I mean, the big problem with Frechet geometry is that you don't have inverse function theorem, you don't have Frobenius theorem, so you need to find replacements or use sometimes Nash-Moser theorem to show that you have a version of inverse function. This can be done, so in many cases, I mean, it's recent work of Neb, Dietz, and other people. So let me comment a little bit on this. So this G naught is defined by this condition, okay? So I have this boundary piece, and I look for gauge transformations that annihilate it at every point. This condition might depend on higher jets. So in this case, it's simple because Xi is this only depends on Xi's, but I could have something that depends on, I don't know, second derivative of Xi. And then, well, I will have some condition for G naught. So G naught is more general. So the G naught that always works, so to speak, is more general than just trivial gauge transformations at the boundary. There is also multiple subgroups in infinite dimensions whose zero-level set of the associated momentum map is exactly C. So this maximality requirement that I talked about before is important. Otherwise, you could take, for example, all gauge transformations whose support is in the interior, and these will not be maximal, and you will have problems later. From a physical point of view, if you just stop at the first stage reduction, well, you don't get observables. These functions have a residual gauge action. Okay, so these are not gauge invariant. So are these observables? It's a philosophical question, perhaps, but okay, from a mathematical point of view, it makes sense to quotient. So we go to second stage reduction. In many cases, this first stage reduction is Frechet smooth. Okay, so this is a fact. And this means that reduction with boundary does in fact improve the regularity of the moduli space. It's going to be infinite dimensional, but okay, this is life. At second stage instead, we expect way less regularity, and smoothness is generally going to be unlikely. But let me still explore the best case scenario here. And why is this relevant and sort of meaningful? Because we have all of the higher structure that can come into play and help us resolve non-smooth quotients, okay? So ultimately, I want to resort to this technique, but let's see where we can get, as far as we can go. Okay, so let's look at the second stage, which we suggestively call flux superselection. So from the first stage, we have a infinite dimensional Frechet weak symplectic manifold with a Hamiltonian momentum map, which is weakly equivariant if I had this cocycle supported on the boundary, which we can treat in the usual way by taking central extensions. The physical point here is this. Now, I do not have a preferred value for the momentum map. Remember, here, the momentum map has a preferred value, which is 0, because I want to fix the constraints. I want to say constraints are 0. Now, I don't have this anymore. So in principle, I have to look at more zero values of this residual momentum map, which is small h. So by adopting Hamiltonian reduction, in this case, I take a coadjoint orbit inside, this should be G underline, sorry about that. I take a coadjoint orbits inside the residual gauge group, the dual, and I take the pre-image and I proceed to do orbit reduction. I call this a flux superselection sector if everything works out, okay, and these are conditions that can be checked, this is going to be smooth or not. So the second stage, the fully reduced phase space, is in fact now only a Poisson manifold. I should comment on this. And it's foliated by these sectors. And these sectors are labeled by the coadjoint orbits of the residual gauge group action, which is something that is supported at the corner or boundary of the boundary. So now the functions over these symplectic leaves are observable because we have quotiented everything. And we can look at, sorry about this problem here, we can look at the Casimirs of this Poisson structure, so the center of the Poisson algebra associated to this. And we expect, but obviously this is hard, we expect that it's precisely the Casimirs of this Poisson structure that will inform the Hilbert space decomposition that people call quantum superselection sector in algebraic quantum field theory. Obviously, to make sense of this, one needs to show that quantization commutes with reduction in here, which is obviously going to be very difficult, but in the case of Chern-Simons, for example, this has been done many years ago by Meinrenken and Woodward, who proved the Verlinde formula using essentially this technique. Okay, let me summarize the reduction by stages for gauge theories. Here I have this geometric phase space, which is just restriction of fields to a codimension 1 submanifold. And then I have first imposing the constraints, and then I need to look at all possible values of the flux. So this momentum map residual. Are there questions before I go to the example of Yang-Mills theory? Okay. So I want to apply the previous procedure to Yang-Mills theory, but in a particular way. I want to consider a manifold sigma, which is again a cylinder, finite cylinder, which is endowed with a null metric. Okay, so on sigma, I have a metric with a degenerate direction along I, along this interval. Why is this relevant? Well, this is interpreted as a null compact submanifold with boundary of a Lorentzian manifold. Okay, so you should really think of a picture like this, where this is some Lorentzian manifold, and I'm considering sigma here. The main application, in fact, is sigma should be a portion of what is typically called light-like infinity. So this is a null direction in this Penrose type diagram, and I'm looking at sigma as a portion of it. So this problem is relevant because of the following observation due to Strominger, that realized that certain relations in scattering amplitudes for electrodynamics or color dynamics or even gravity are interpreted as word identities for certain symmetries that are non-trivial here. So at the boundary, well, in this case, sorry, here. Then you can push it to the infinity, but and the scattering phenomenon instead happens here. So it's about propagation and detection of this scattering phenomenon at infinity. Soft photon here means, in fact, a non-vanishing electromagnetic field at sigma with arbitrarily low frequency, which you can think of as a zero mode in a Fourier expansion in some sense. While soft word identity, as I just said, relates to certain residual gauge transformations on what people call the Achteker-Streubel phase space, which I will describe in the next slide. And these are gauge transformations that are non-vanishing at sigma and at the endpoints. The final piece of the puzzle is an observable that is called electromagnetic memory, or the effect related to it is the electromagnetic memory effect, which is the net effect of a passing of photons, so a residual of a scattering event, on certain test charges. Okay, so these three items, these three pieces of the puzzle seem to be slightly unrelated at this point, but okay, they have been related by Strominger and then later by Strominger and Pastersky. We do it from a Hamiltonian point of view, and we define the geometric phase space induced on sigma by Yang-Mills theory as a space of connections, which I split as connections along the interval and something residual, together with generalized electric fields, which are just top minus one forms over sigma, exactly in this sense. So the geometric phase space is given by these sort of I connections, so these AU, DU, and these spatial connections, which will play an important role, together with electric fields. This is the symplectic form, and I have a gauge group action, which is just the usual transformation of connections and elements in the joint. Okay, so this is just a geometric phase space. Now, historically, another phase space has been introduced to treat this scenario, which is the Achterker-Streubel phase space, which is given by, well, this formula. So you just pick out these spatial connections over here, and you consider this symplectic form. Now, I would like to point out that this symplectic form depends on derivatives of fields, okay? So in the lingo, this is non-ultralocal, which is a peculiarity of this situation. There are other phase spaces that have been considered in this setup. One is an extension of this Achterker-Streubel phase space by the cotangent bundle of gauge transformations at the corner sigma S. So this is S, this is S, and sigma is S cross I. Okay, so you take one copy of the boundary sphere and take maps into G. Cotangent bundle, this is symplectic manifold. You can extend this in this way. Or you can do it linearly by taking the Lie algebra instead. Okay, so in this setup, we have several symplectic spaces. Which is the correct one? We don't know. One observation is that you can obtain the Achterker-Streubel phase space out of the geometric phase space by what people call a gauge fixing, which is just requiring that this connection AU vanish. So this is a legitimate operation that you can do, but what is its meaning is slightly unclear from a geometric point of view. Okay, so this is just the kinematics, so to speak. The dynamics of the problem is specified by, well, Noether's current, which again is the same, right, that I produced before, but now I have to write it in this language, in these coordinates. So this is just explicit way of writing it. So the constraint set is just the zero of the bulk part of the Noether current. And the fully reduced phase space, as we know, is just C modulo all gauge transformations. Okay? As a setup, I need one last piece of terminology. Since we have two boundary components, which we can think of as an incoming and outgoing or initial and final spheres for this cylinder, I'm going to denote vector valued objects as initial, final, or their difference if by using this language. In particular, if I parameterize the Lie algebra, the mapping Lie algebra at the boundary of this sigma manifold using this language, I can rewrite the flux form in this way. Okay, so here is our result. Applying the construction that I discussed before, Young-Mills theory with a compact non-abelian structure group G, we have that G naught is the identity component of the relative mapping group. And we have a local symplectomorphism between the true constraint reduced phase space and this extended Ashtekar-Streubel space. This is all very explicit. And over it, there is a residual Hamiltonian action, which is also very explicit, with the following momentum map. Well, okay, so this might not be particularly illuminating, but it is an example of a momentum map over a Frechet manifold that is, non-trivial. In the abelian case, we have a very similar result, but now the symplectomorphism becomes global. Okay, so I really have that the first stage of this reduction is given by this extension, and I have this momentum map associated to the action. Here, G naught is again the identity component of the relative mapping group plus constants. So this G dot means that I'm also considering constants in the mix. Now, we have done first stage, and then we expect to have a second stage, but the residual group action is given by the mapping group at the two boundary components of this sigma null manifold. So what we can do is we can apply reduction by stages again, and first reduce by the incoming group, and then be left with whatever is left. This is how one gets the Ashtekar-Streubel symplectic space, in fact. The partial second stage reduction of the Yang-Mysterin on a null surface produces exactly the Ashtekar-Streubel symplectic space if you set the initial electric field to 0. Otherwise, not. There is a residual Lie algebra action of the final copy up to constants, which is exactly the soft symmetries that Strominger has introduced. And the momentum map of this Hamiltonian action is the electromagnetic memory. The electromagnetic memory, which was introduced by Beery and Garfinkel, is in this abelian case just the difference of the electric field at the two corners, here and here. And by writing it explicitly, using this parameterization, you get that the memory, which is really the difference of the electric field, is precisely the momentum map. So what this does, how much time do I have? Okay. What this does is it tells us that, well, first of all, the easy relation between soft symmetries and memory are encoded in the fact that we have a Hamiltonian action in this Ashtekar-Streubel phase space, which is obtained as a partial symplectic reduction. The fact that the momentum map is preserved by the dynamics is the statement that people usually look at of conservation of soft charges. And the potential result of quantization commutes with reduction should be, but this, still heuristics, should be the motivation for why soft theorems are true. As a byproduct, we can explain this gauge fixing operation as a gauge fixing, but for which gauge group? The gauge group of gauge transformations that are trivial only at one boundary component and not both. Which, if you ask me, is fairly not natural as an operation, but okay. Now, a somewhat philosophical point here is that here in the abelian case, we get an observable momentum map, a surface charge, as Maxime was saying, but for what? For a gauge symmetry. This, if you think about your first course on gauge symmetry, you know that this is not possible. Gauge symmetries have zero charges up to boundary. Right? So it was already encoded in Noether's theorem, right? Noether's theorem tells you that it's the de Rham class of the Noether current that vanishes on shell. So it may have a boundary contribution. Okay, I think this point is underappreciated, but okay. By the way, I mean, this is this is my point of view, okay? I guess people have said that this fact is explainable in the sense that gauge symmetries become physical, become sort of global or observable at the boundary, which is maybe the same way of, another way of saying the same thing, but okay. Is there a non-abelian generalization? Yes. Just very quickly, you can do exactly the same procedure. You can fix, take the component of the momentum map for a normal subgroup given by the initial copy of the mapping group. And you again get the non-abelian Ashtekar-Streubel phase space with a residual Lie algebra action, which is again soft symmetries, but in the non-abelian case. And now the momentum map is what we call non-abelian memory. It's this object. But I should maybe say that this is slightly different from the proposed non-abelian generalization that goes under the name of color memory by Pastersky, Raclario, and Strominger. What's the point here? This object, being a momentum map, is gauge equivariant. This color memory is not gauge equivariant, is actually not invariant, not anything, because it's a linearization of this. They know what to do with it. This is another statement. Okay. So let me draw some conclusions here. It's an old story, but still true. Noether's theorem tells us that in some good cases, we have a Hamiltonian reduction paradigm on codimension 1 hypersurfaces of a gauge field theory. However, if that hypersurface has a boundary, there is a mismatch between the zero of the Noether current and the constraint set. So the new adjusted paradigm that we propose is that, well, in codimension 1, you assign a symplectic space, which is this first stage reduction, and in codimension 2, you assign a Poisson space, which is the second stage reduction. If quantization commutes with the second stage reduction, then you prove the existence of a Hilbert space that decomposes into sectors as predicted by algebraic quantum field theory. In the particular case of null abelian Yang-Mills theory, this is the structure that you get. If you want to obtain this Ashtekar-Streubel phase space, which is central in the investigations of in physics, well, you need to work a little bit more. So you need to split this second stage reduction into two pieces. Well, globally, I mean, overall, you have a momentum map which splits into two components. One is the electric field at the initial boundary, and the other one is the difference. This obviously in the null case, in the abelian case. I think I'm done. Thank you.
I have a question about this quantization commutes with reduction, because in many cases when people refer to symplectic to symplectic, but here is symplectic to Poisson. So what is it exactly what you expect?
Well, okay, so here what you would like to have, so you have a symplectic manifold. Let's say that a quantization of that symplectic manifold exists. And then, sorry, let me write down something. So you have a Poisson map between the first stage and the second stage. This is symplectic, this is Poisson. Now, up to very important subtleties, you can look at, you can pull back the center of this algebra over here, and you can map it into the subrepresentation coming from functions over here. So that subrepresentation will have a center. So if you have, this goes to a Hilbert space, but there is a subrepresentation. Now, this subrepresentation will split into components, right? The other thing you could do is you could take the symplectic leaves inside here, and you can quantize these. These are symplectic. So you expect these symplectic leaves to quantize to the component of the Hilbert space, right? So in this sense, is commutes with reduction. Sorry?
In physics literature, people usually use your asymptotic symmetry.
Right.
So in your language, these are generated by the second stage.
Correct. Yeah, so these are asymptotic only if you really send this to infinity, but so the main concept holds also at finite distance, which is also something that is perhaps not really appreciated. This whole story is finite distance. Then, in the particular case of 4D Yang-Mills, which is conformal, you can send everything to infinity and the results still hold. But otherwise, it's non-trivial. But the phenomenon is already there at finite distance.
But usually when we speak about asymptotic in the sense of infinity, we just conform infinite.
Sure, yes, yes, sure. Sure.
In your general setting, you assume that there is this full propagation transformation acting on the space of fields, right? This can be restricted in
Yes.
examples, right?
Thank you for the question. So in the Poisson sigma model, what you can do is you can look at an algebroid over the shell. So over C, because C is coisotropic inside the geometric phase space, you always have a Lie algebroid. This is always given. There's always a Lie algebroid. So then what you can do is you can try to look at Hamiltonian reduction for this algebroid. In the Poisson sigma model, the first stage is by Cattaneo-Felder, is the space of A paths over A homotopies, and this is the symplectic groupoid. First stage. which means that you expect there to be a second stage acting over the symplectic groupoid, which should return to you the Poisson manifold that you started. Yeah. So, in fact, yeah, this is a generalization of the setup. But for this generalization to work, one really needs the notion of Hamiltonian Lie algebroids. Everything is bundled, all the conditions, the G naught now becomes a bundled version of the definition that we had before, and there are non-trivial issues with even the notion of what it means to reduce an algebroid by a subalgebroid.